Okay, so good afternoon everyone. Um, so we're going to kick off from where we left off at the last lecture, where we had looked at the calculation of signal to quantization noise and come to the conclusion that this equation here that we can see is an important one in terms of A to D conversion, because it tells us the signal to quantization noise ratio, so how much digital noise is introduced, and it's dependent on the value of n, which is the number of bits in the system. So as n gets bigger, the signal to quantization noise ratio gets bigger as well. And we got to the point where we said that 16-bit system, we can calculate the SQNR to be 98 dBs. So this is only the case though for a maximum input signal. If you put in signals that are smaller than the maximum, then the noise is higher. But we have to have something to measure against. So there's this concept of oversampling. Let's get rid of me now. And oversampling allows us to improve the signal to quantizer noise ratio, but we're going to have to sample faster and quicker than the Nyquist frequency. So we just have a quick, it will be very quick, reminder about noise, power, spectral density, and how that sort of applies going forward. So a noise source, and in this case it's our quantization noise, which we're going to assume is sort of random and Gaussian, which is not always the case. Generates noise across the spectrum, and if we feed this continuous signal into our quantizer, we get out our output signal, which has quantization error on it. And we know that the total noise power in the band is going to be q squared over 12, because we calculated that a bit earlier. So this is a complicated way of just saying that the noise is spread equally across the band that we're measuring across. And it says the power must be spread evenly throughout the signal bandwidth because it's random, and therefore its probability of error is equal across the whole bandwidth. Probably easier to see if we look at a picture of it. So this is the sort of the probability of error or distribution of error across the signal bandwidth. So the signal bandwidth is the sampling frequency divided by 2 for a Nyquist. So this is the sort of single-sided area for our message. So you can see the noise height is constant and it's spread across the whole area. So this is relatively straightforward. If we're interested in power, then we square it. And then we've got this thing which is just basically squared, but we know that the total power is q squared over 12, so the area of this section is q squared over 12, so we can start to then put some numbers on the heights of these things and work out the value of k in this case, or whatever. So the noise spectral density is equal to k, which is q over root 12 times 1 over root fs, or the noise power spectral density is just that squared. So this is a measure of the noise in the band that we're interested in. So that's all good. If we then increase the sampling frequency, and this is where it starts to get interesting, the amplitude of the quantization noise power must decrease, because if we increase our sampling frequency to, say, here, from original over here, the area in this area here must be the same as the area that it was before. Because the noise hasn't changed and the noise has been spread equally across the band. So by sampling at a higher frequency, we reduce the noise floor, if you like, down. Now our signal bandwidth hasn't changed. This is still where our message is going to be, but you can see that the level of noise in that band has dropped. So as long as we only keep our signals in this range here, the total noise in our band of interest is got reduced, and we're going to filter this out. We can filter that out. So we've sort of moved some of the noise here up here. That's one way of looking at it. And so that's quite a nice idea. And this is the idea of oversampling. So we sample at higher frequency than the Nyquist rate, and that allows us to reduce the quantization noise floor in our band of interest. And obviously the further we take this sampling frequency up here, the lower this floor will drop down, and the amplitude of the noise in the band of interest, which is just this bit here, will get lower and lower and lower. And the ratio of how much we've got here, or how much we've got here in relation to the whole area, is the oversampling ratio, and it's defined as the sampling frequency over 2 times the bandwidth of the message. Because remember, we need 2 samples per wavelength to get to Nyquist. So 2 FM is the minimum sampling rate for a signal band limited to FM, i.e. 2 samples per period. So in the case of a Nyquist converter, this means that 2 FM is equal to the sampling frequency, and therefore the oversampling rate equals 1. And that makes sense, because for a Nyquist frequency we're not oversampling. So sampling ratio 1 makes perfect sense there. And so if you want to formalize this, you can effectively say that we're going to have to integrate the noise over the whole area, and we know what it's a very simple calculation in many ways, but if this was a weird shape, then we'd have to integrate it properly. And then we've got the band of interest, H of F, which we normally take to be this sort of just block here, so it's our filtered response. So it's the filtered response of our bandwidth, and we'll assume in this case it's just a brick wall filter, but it would roll off, and this will be the frequency response to the roll off. And you multiply that out in these simple cases, and we end up with the noise power in the band of interest is given by Q squared over 12, which is what we had before, but then divided by the oversampling ratio. So that's actually quite a simple calculation from what looks like quite a complicated sum in the first place. So as Fs is increased, as we move this point out further, the amplitude of the noise in this area gets lower, and which is what we've just said in the previous slide. And so we've actually got less noise in our band of interest, assuming we can filter this out, but we've obviously upped the sampling rate, so we've got a lot more data than we had before. But that's okay. That's maybe a trade-off that we're interested in doing. So from the previous slide then, the new quantization noise power in the band of interest is given by Q squared over 12, which is what it was before, divided by the oversampling ratio. So if we sample higher, the power in the band of interest goes down. So if we just throw that into our signal to noise equation that we developed earlier, so this is the signal which we got from earlier slides, which is filling up the entire dynamic range with its amplitude, and then we divide it by the noise power, which is just this equation here. We then get a very similar equation to what we had before, 3 over 2 times 2 to the 2n, this time times OSR. So if we expand that out and do the log business, we end up with this kind of thing, and we end up with 6.02 plus 1.76 plus this other term here, which is 10 log OSR in dBs. So that's improved the signal to noise ratio by this oversampling ratio factor. Thus, if we doubled the oversampling ratio, we would end up with 3 dB improvement of the signal to noise ratio, which is about the equivalent of about half a bit or so in terms of N here, which is a useful result to have. So oversampling is a good idea because it takes all kinds of problems away. First of all, we don't need to have this anti-aliasing filter that's got a brick wall response. We can be a bit more lenient about it, but it also allows us to actually reduce the signal to quantization noise ratio as well. So this is all good. Right, so we bear that in mind because that equation there becomes really important when we will look at the sigma delta converters and we do something called noise shaping. So this applies just for all standard converters, but we can do something clever with that a bit later. So just some basics then. So we've looked at these types of specification: number of bits, sampling rate, and the signal to noise ratio, which allows us to get a good idea of the sort of performance we might get out. There are some other things that we just really briefly need to discuss. The relative accuracy, that's the deviation of the output from a straight line drawn through 0 and full scale, and we'll look at a picture of that in a minute. Integral nonlinearity, again a picture will show us that. Differential linearity, again we'll look at that as well. Each step size variation, ideally each step is 1 bit, but in practice the step sizes can vary significantly, and so 1 bit at one level may not be the same as a bit at the other level. This is obviously a bad thing. And usually this linearity is designed to be better than half a bit or so between them, otherwise we end up all over the place. And again, a picture will show us that. And we would also like these things to be monotonic, which means there are no missing codes in the output. So we can't jump a code when we have an output. Again, it's all been shown by these graphs here. So if everything is equal and equally spaced, whatever, we can run a straight line through this thing, and we've got a one-to-one match from digital code output to analog signal coming input, and that's nice and linear. There's obviously a bit of an offset error in terms of where this staircase is zeroed, but we have, but if it's in this position here, this is almost sort of perfect. If we get a staircase that's pretty good, but the slope isn't 1, then we end up with an error in terms of linearity, so we're not getting a one-to-one match from the input coming out, but it's still linear in the way it gets there. It's just the gain factor is not quite 1. So non-linear differential non-linearity is when the steps are sort of all over the place. If you build a really rubbish A to D converter, you might get a response like that. So effectively your input to output characteristic is this curve, and it's non-linear, and there's various ways of trying to measure that. You don't see very much of this these days. And non-monoticity is when you're going up in the stairs, and in fact this one you've gone down a stair before coming up again, and that's a really not a very good design system. So these are things that people need to be worried about, but look, they originate from component tolerances in the device themselves, temperature sensitivity, noise in the system, all that kind of stuff. So you might actually have something that starts off like this, but as temperature gets hotter and tolerances and things change, it might turn into something like this. So you have to be aware of that and look for those specs in your data sheets. It's usually worse if you build these things yourself from scratch, but people don't tend to do that these days very much. But you never know, one day you might have to. So we've got there's an example here that allows you to work out how many bits are required for something. What I'm going to suggest we do is skip over this example because it's just applying the equations, and it should be relatively straightforward, and you can have a look at that in your own time, because I'm quite aware that we're running out of time to deliver this material, and I want to get on to the interesting stuff, so we've got time to look at that. So again, this is the same example, so it's all straightforward, the answer's there, so I just suggest you have a look at that in your own time after the lecture. So that moves us on to types of A to D converter. So you'll have done some of these with Alex in part 2, but we'll just run over them quickly for completeness. So the counting A to D converter, this is a DAC, but it's an A to D. It requires a comparator and a DAC, so digital to analog converter, and we end up with a structure like this, and this is a comparator, so that just gives us a high or a low output depending on whether the signal here is higher or lower than this input going on here. So our input signal comes in, and we assume that's not moving very much, so we've got almost like a fixed input voltage here which we want to digitize, and then this counter just counts up and down on the input of a clock, and the direction or the reset is controlled by the output of the comparator, and so as the output clocks up, the output from this digital to analog converter will rise, and when it crosses over the threshold of this, the output of this will ping the other way and it will stop the clock, and that allows us then to get an output. If we read this register here, that tells us the digital version of the analog signal, and then we just reset it and start again, and it counts up. Easily what's seen in this kind of arrangement here. So we've got a signal coming in that we're interested in. We start the conversion, we start clocking up the counter, and when it reaches the level, we stop the clock and read the reading out. Obviously, this works quite nicely, but high voltages take longer to digitize than low voltages. You can see here the time to conversion, if you like, is a short time, whereas here it's a long time. So it's non-deterministic in many ways, but with a bit of playing around with the logic in this, you can actually make a tracking converter. So instead of making it stop and drop down again and start counting from 0, you can actually just change the output by small amounts in the direction that the signal's gone, and just track it slowly and just read out the difference from the register. And so that makes life much easier, and you can track the signals, and there's not all this messing around of counting up and down. It's the same logic, it's the same principal idea, it's just a little bit of reprogramming in how you work the system. Okay. Slowly varying signals can then be tracked quite quickly, because as they're moving slowly we can track them very quickly. Here signals that are moving a bit quicker are difficult to get to, because by the time we've counted up here, it could have changed quite a lot in this period. It could have gone right up and messed around a bit. So something that tracks quickly is a good idea, and if you haven't got to move very far, then you can track things quicker. So a variation of this, which tends to be the one that's used a lot more, is a successive approximation system. So we've got exactly the same kind of layout, only that we can control the logic a little bit more, with a bit more detail in here. So it's the same kind of principle applies, but the difference in this case is that the time to completion is fixed, because we test each bit individually, and it depends. So the more bits we have, the longer it's going to take. But we start by setting one bit, and that gives us a voltage on the output here, which we can compare against this input. If it's if the voltage is this is the test voltage along here. So if we then plug in the most significant bit and see what voltage comes out here, if it's above that voltage there, we would set bit 3 to 0, subtract that voltage, and then move to the next bit, see where that goes, and eventually successively approximate this until we get something that's close to it. And at the end of that time period, when we've tested all these bits against the output voltage, we just read out the value of this register again. So conversion here takes n cycles to complete, where n is the number of bits, but it's fixed, so it's completely deterministic. You can start conversion and know when it's going to finish. Maximum resolution is fixed by the DAC, so that needs to be the performance element in this system. This needs to be settled down and sorted out before we take a reading in here. Typical number of bits for these kind of systems is 10 to 12 as a maximum. Above this, we start to have very high performance other components, such as the DAC needs to be very high performance, and the comparator also needs to end up being very high performance as well. In terms of speed, we end up with a few mega samples a second, and this sort of depends on the resolution. But one of the attractions is that power consumption of these type of systems scales directly with frequency. So at low frequencies, when you're clocking it slowly, they don't use much power. And they are very small in terms of silicon, because they're quite simple to actually implement. It's just a bit of logic. And so they can make very compact systems. So there's a lot of attraction to this type of system, but there are some downsides as well, as they're not particularly fast, and the more resolution you get, the longer they take to give you an answer. We can start to combine some of the techniques that we have got some interest in now. So it says here that a bit of thought can show that instead of setting the output of a DAC to try and match the input voltage Vin, the sampled voltage Vin can itself be modified and compared with naught. It's just the other side of the same coin, really. And we can do that with a charge distribution approach using switched capacitors. So these switched capacitors have appeared again because we can implement very good capacitors that have a tightly controlled ratio between each other. And this is quite neat because it allows the sample and hold, the DAC and the comparator function to all be combined into one lump, which is effectively what we've got here. So the way this thing might work, and again I suspect the speed we're going, you're going to have to sit and think about this, but it's quite logical in many ways how it works. So in sample mode, when we're going to sample the signal, we charge the capacitors to Vin, so the input signal comes in and they're all charged to the same voltage, all these capacitors, while the comparator is reset, so that's all set there. And that's the equivalent of sampling and holding, because we've just sampled the input voltage and stored a charge on all these capacitors here. And in hold mode, the comparator is taken out of reset, so it's now turned into a comparator, and all the capacitors are switched to ground. So we switch all these capacitors to ground now. So remember, they're all still holding a charge, and they've all got the same voltage across them, And now, because they all have to maintain their voltage because they're capacitors and the charge hasn't been allowed to go anywhere, we end up with this polarity switch. So it's similar to what we looked at in terms of the inductors and the switch mode power supplies, and also for the switch capacitances when we were messing about with negative supplies. So we're doing the same kind of idea there. It's got the same voltage across all these capacitors, and so the this now pings down to a different voltage. So that's our sort of sample and hold, and then VREF is selected, so the reference voltage that we're going to be comparing against, and we can then start to switch each one of these things through and compare the voltage. So VREF is now coming through to here. That gives us a voltage shift over here, and this voltage here then moves by VREF over 2 in this case. And that depends whether or not that triggers the comparators, not as to whether we get a bit out of it. So that's how that's going. So then we will switch that back, switch this one in, and we'd end up with a slightly different equation, but effectively we're still testing this significant bit against the whole voltage stored on these capacitors. And we get the voltage out then from the successive approximation register over here. So there'll be a whole. So we'd have to switch the input to the different parts of the register to get each bit as we're doing that. But it's all switchable. It's all under the control of a clock, and it's all easily integrated and gives quite a neat way of implementing this type of system. The other type, which I know you did with Alex as well, is the dual slope ADC. And this is quite nice because it allows quite a simple system to give us a high resolution. So we can get up to about 14 bits with this system if we wanted to. But it does tend to be slow. But it has some other advantages, as it's effectively an integrating system. So if we integrate noise, then the average noise becomes, well, if it's Gaussian noise, hopefully it becomes 0. It's better matched to low-level signals because of this as well. And they're used a lot in voltmeters to measure voltages in test circuits. So it's a timing process. The operation involved integrating the unknown voltage, so the one we're trying to measure, so V in, we would integrate that for a fixed period of time before deintegrating the voltage against a known reference. So we switch that around and take the charge out, so they have to be opposite in sign until the output is 0. So this is the integrator here. So we're just going to integrate this voltage. This voltage will ramp up over time depending on what the voltage is here and how quickly this capacitance charges. It'll eventually hit the level of this comparator, switch the logic, and it will switch this over and start to discharge the capacitor from this other voltage, and the ratio of the two times becomes an indication of the ratio of V into VF. So we get this kind of idea. The variable slope, so whatever V in is over here, it will charge up the RC or the capacitance in this RC network at a rate depending on the difference in voltage across this capacitance. So a small voltage in here gives us a low charging rate, but it's linear because it's an integrator, and a high voltage here gives us a much faster charging rate, or at least it charges to a higher voltage in a given time period. And at that point we then switch to VREF. We're not switching, I want to switch to VREF over here. VREF is known, so the slope that it will discharge at is known. So this is a known entity here, and when it crosses back to 0 again, the whole system stops. So we don't know this, but it counts up to a point, charges up to a certain point, and we measure a fixed period of time, and then we switch the other way, and then we will measure the time needed for it to discharge at a known rate. So this is a known rate going on, and you can follow this through with some basic maths if you want to, but hopefully we've done all that. And if you do that and follow it through, and one of these has to be negative, so this won't work as it's written, we end up with an equation that says that T1 over T2, so this period here compared with whatever this varying period here is equal to the ratio of VREF over V in, and we know V in is the thing we don't know. And as time is being measured by a counter, we're just counting up, it just becomes the ratio of two counts in this counter. So we count for this period and we count for this period, and the ratio of those two counts is the value, and that's a really easy thing to implement in a microcontroller or even just some logic, because things like this just count for a living. Okay, so that's a really nice technique. It's a bit slow, and the resolution becomes on how fast our timers become as well. So we can, if we run a really fast timer, then we're okay, but we still need a finite and measurable period of time in these areas here. And the time itself is not fixed because it's variable depending on how high we get up this curve here. But for slow moving signals and accurate numbers, where you're not fussed about the speed at which you're converting it, it's a really nice and easy system. And if you want to go the other way, if you want to go really fast, you tend to have a system then that hasn't got much in the way of resolution, because things start to get complicated. And the flash converter is a brute force method. It's the fastest converter, but it's difficult to get high resolution from it. So a full conversion of however many bits you've set this thing up for can be achieved in one clock cycle. So that's as fast as it can get, really. But it does require a system of calibrated resistors and comparators. And basically we've got a system like this, where Vin comes through here and is compared against different threshold voltages in each comparator. So we've just got a fraction of the reference voltage being tapped off at each of these points for the comparators. And then as the voltage here is varying, we end up with some of these being switched and then others not being switched. And so we've got this what's called a thermometer code here. At some point it will switch from 1 to 0 at these inputs, and that is then multiplexed into a logical number which we can then read out. So this is the structure for a 3-bit converter. There's a resistor chain that provides sample points for each possible level, as I've just explained. And a 3-bit converter requires 7 levels to give us our total 3 bits of resolution. So in general, an n-bit converter will require 2 to the n minus 1 comparators, one for each level, and therefore 2 to the n resistors as well. And the resistors have to be the same as each other. So when you start to get to 2 to n of these things, when n is say 8, that becomes 256. You've got 256 resistors to worry about, all of which have to be the same. As I said, it can be visualized as a thermometer, and it's called a thermometer code, as presented to the logic block. So these will be 1 1 1 1 1 0 0 0 0 0. There won't be any 1 0 1 0 1 0s going on, and that can then just be turned into a logical number, or a binary, or a decimal number, binary coded decimal, whatever you want. So that's nice and quick. Occasionally, because this is a fast signal, we're interested in transients as well. So if there's a fast moving signal, or even some noise, or indeed problems in settling the comparators, if we've got these a bit wrong and the output bounces before it settles, you might get an illegal code generated. So for example, a thermometer code of 11110000, which is what this is settled down to, you may read it as 11110100, because one of these comparators here has maybe bounced a bit, and at the time of sampling you've read it when it's been a 1 rather than a 0. And that is called a sparkle or a bubble code. So you can imagine there's a level here, and then there's a bubble of a 1 in the wrong place. And that's something. So this is where the performance of these circuits becomes important, because you don't want these sparkles or bubbles occurring, and it's entirely down to a speed thing and a balance thing. So you might want then to actually add a track and hold to the output of these comparators, or even to the input of these things here. So you can easily see that even this simple idea can start to get more complicated when you really start to push the limits of what's going on. But what we end up with is, for every increase of 1 bit, there is a doubling of the number of components needed, leading very quickly to very complex circuits. In addition, the matching or accuracy between components needs to be increased. And a flash converter is usually limited to 8 bits of resolution or so, but can have very high speeds. So if you looked at something like the MAX 108 from Maxim Semiconductors, it's got a 1.5 gigasamples a second sampling rate and 8 bits of resolution. So the resolution, this is pretty much state of the art for a couple of years ago anyway. 8 bits of resolution is not huge, but 1.5 gigasamples a second is a lot of data. Of course, you've always got to assess whether you need this level of performance or not, because this 1.5 gigasamples a second means that these points here are changing at 1.5 thousand times a second. 1.5 gigacycles is going on here, and you've got to read that data out and do something with it in that time period. So you've got huge amounts of data flying out of this thing, and you've got to do something with it, and you haven't got very long to do anything with it. So you might even struggle to even store it onto any memory unit. So you've got to be selective about what level of performance you really need, because not only does this have to be high performance, but anything you connected it to also has to be high performance as well. Right, so that leads us on to an interesting collection of systems, which are sort of called half flash or pipeline converters, or sort of hybrid systems. It's trying to compromise between the speed and circuit complexity. So there's all kinds of, it's a very active research area. People are all looking for all kinds of clever ways of trying to get speed and resolution and reduce the power and everything else that goes with it. So this is one sort of idea that people have been using. Here the analog voltage is converted in 2 stages. So we've got analog coming in here, and we've got a 4-bit flash. So a 4-bit conversion is not a hard thing to build. But we also need a 4-bit DAC that's equally fast as well, which is then added back in, subtracted from here, leaving us with the small half of the signal. So this takes out the big half of the signal. We then subtract this from it, and that leaves us with a small half of the signal, and then we can do a 4-bit flash on that as well, and that leaves us with an 8-bit flash converter that's been done effectively in 2 chunks, because we can't do all this simultaneously. So we do this bit first, we allow this to settle, we subtract this from here, and then we trigger this one. But we can do it in a few clock cycles rather than 1 clock cycle, but we've reduced the complexity of the circuit in terms of the number of components we need by a huge amount. So so the words say as coarse conversion to 4-bit resolution is done. That gives us the most significant 4 bits. That's happening over here. And the analog equivalent for this is then subtracted from the input. So we've got a subtraction amplifier going on here. So there's an analog device hidden in this summing junction. Another 4-bit conversion is then done on what's left over, and we have to reduce the reference voltage accordingly, because we're talking about smaller voltages. And these then add up to give us the 4 least significant bits of the system. If we did this with a pure flash converter, we would need 2 to the 8 minus 1, 255 comparators. In this case, we'd only need 2 to the 4 minus 1, because we're doing a 4-bit conversion, but 2 of them, and that gives us 30 comparators. So in this system, instead of having 256 comparators, we're down to 30. And what we've done is we've traded a bit of speed, because best we can probably hope for to do this system is 2 clock cycles, probably a few more. But even so, it's still pretty quick, and then we can grab that information and throw it out onto the logic bus. So that's quite a neat sort of system. And then if we really want high resolution and reasonable speed, but it's tricky to get the speed and the resolution, there's this neat thing called a sigma delta converter. And a sigma delta converter takes the idea of oversampling to an absolute extreme. It only uses a 1-bit converter, which is a comparator, which is really helpful, because the linearity is guaranteed at that point, because we've only got 2 bits, only got 2 points on a 1-bit converter, high and low, and it's not possible to not draw a straight line between those two. But the sampling rate goes up really high. So for example, 256 times Nyquist is sort of typical. And by combining these 2 ideas, it's not obvious how it's combined at the moment, but if we combine those 2, we can get a very high resolution conversion of up to 24 bits, which is crazy high resolution. And in practice, no one ever uses that resolution, because the analog circuitry and the filters and everything that has to go with it just can't match that level of performance. But as a marketing exercise, to say that you've got the highest resolution converter, it's a good thing to be able to do. So to get an idea of how this works, because it's quite neat really, if we consider a 1-bit A to D converter, which is effectively a comparator, and apply our signal quantization noise formula blindly to it, just to see what's going on, we end up with a signal to quantization noise ratio for such a thing of 7.78 dBs, which is a bit sort of hopeless in many ways. That means an awful lot of noise in here, and it's difficult to even see how a 1-bit comparator can actually work. But we can still get a number out of this, and it's a low number. Whereas for a 16-bit system, we would obviously hope for something much higher than that, 98 dBs. But this idea of oversampling becomes interesting then, because remember, if we increase the oversampling ratio, we could add extra. We could improve the signal to noise ratio of our system. And we had this conversion factor of 10 log OSR in there. So assuming we can get an oversampling ratio, we can modify this equation to give us this, and then we can work out what oversampling ratio we would need to give us the equivalent of a 16-bit A to D converter quantization noise ratio. And if we do that, it comes out to be a stupidly large number. If we could oversample by a factor of 1 times 10 to the 9, in principle we can get a signal to quantization noise ratio which is comparable to a 16-bit system. And remember, this is for a 1-bit comparator, just sampling really fast. But so fast it's just impractical. And it's still not completely obvious how it works. But if we just put that to one side for a minute, we can then say that given an input bandwidth of say 25 kilohertz for a reasonable audio signal, this implies a new sampling frequency of 54,000 gigahertz, which is very high, but the concept is tempting. So this allows us to get the noise down. So we can maybe look a bit further into this idea and think about something called noise shaping. And noise shaping is a really neat idea that works in the digital world, which allows us to move noise, digital noise, from one part of a spectrum to another. So what we could do is take the noise in the bit of spectrum that we're interested in and put it into a higher area which we're not interested in, and then just filter it out. So that's an interesting concept. So hold that idea that we're going to move noise from one end of a frequency spectrum to the other end. So the average noise is still the same. We haven't done anything particularly magical, we've just moved it somewhere else. And then as long as we can filter that bit away, which we can do because we'll have separated the signal from the noise, we can improve the signal to noise ratio, only for digital signals. Another advantage of using a 1-bit converter is the inherent linearity. Something funny happened there, so I hope I haven't been talking to myself for a while. Anyway, as I previously mentioned, the 1-bit converter is inherently linear. It cannot be anything other than linear because it's only got 2 output values, and that's the minimum you need to define a straight line. So we've got this idea that signal to noise can be modified by sampling rate, and we've got this 1-bit converter. It's not completely immediately obvious how this might work as a converter at the moment, but let's just go further. So let's just consider this structure. So we've got signals coming in, they're going through some kind of filtering function here, they're getting quantized, and there's a bit of a feedback going on. And this is the general feature of a noise shaping modulator. So you can sort of follow it through. We just have to accept that we've got samples coming in, going through a filter, converted to something else, they get quantized or compared, if you like, are they high or low, and that gives us an output signal which is then fed back in itself and added to the input signal. So H of Z is usually a form of an integrator or a low pass filter, and the whole point of these feedback systems in general is the output tries to track the input by giving out pulses, either positive or negative, that show if the input is higher or lower than the sum of the previous pulses. And this is where the sigma delta name comes from. I've got a picture of this actually happening in a minute, which will maybe clear things up a little bit. But to do this properly, sadly we need to have some idea of the Z transform, and every year there's no guarantee that everyone understands the Z transform or even heard of it. So we don't need to go into the details of it particularly, but we just need to understand that it exists and have some of the features for it. So it's a mathematical transform, and it's very similar to the Laplace transform, and it's particularly applicable to sampled systems, and the Laplace and the Z are actually quite closely linked. So what we really need to know is that there's this thing called Z to the minus 1, and that is called a time delay operator, and it effectively denotes the sample delayed by a time period or sample period. So this is our sort of sampled signal where we're sampling at t, and then at the next t period, and we would mathematically define this as being sampled with this impulse response, and we would add that up and say the whole signal becomes this summation. If you do the Laplace of that, we just replace it with e to the minus s of t, wherever t is, and that adds up to give us that. And then all we do is we actually replace e to the st, or e to the minus s, e to the st, with z, and that is, in a nutshell, the z transform. So it's just replacing the exponential with this delay term. So it's a simple thing. Mathematically it's a lot more complicated than that, about what it actually means, but it's a useful thing, and for our purposes we just need to remember that z to the minus 1, which is the thing we're going to be interested in a lot, is just a unit delay. So it means it's delayed the sample. So a sample coming into here has been delayed by one time step before being presented at the output here. And these Z transforms are obviously very useful in digital filter designs, because a delay, which is a flip-flop effectively, is a very useful and very simple thing to have in digital circuits. So if we can define all our transfer functions from our time domain in terms of Z minus 1s, which are just delays, then suddenly building transfer functions in logic circuits becomes quite an easy thing to do. Right, so this is the simulation of a first order modulator showing what's going on. So we've got 64 times oversampling here. We've got our input sine wave coming in at a certain frequency. So if this was 1 kilohertz, we'd be sampling at 64 kilohertz. And all we're doing is looking at whether or not the comparator or the output from our comparator is higher or lower than the input signal. And you can see that at 0 points we end up with a lot of switching points, and it becomes the density of these pulses that becomes important. And at low levels, negative levels, the output of our system tends to be quite low, and then as we get closer to the 0 crossing again, you can see we get a lot of crossing points, and then at the high point the output of our modulators starts to stick high, and then crosses over again. And you can see the sort of the levels of these how this sine wave is sort of encoded in the average level of this point. And in fact, if we did low pass filter these pulse trains here, we would get this signal back again, because the average of this is 0, the average of this is high, the average of this is 0, the average of this is low. So it's a pulse representation of the information, so you can sort of see how it's encoded. And if you go up in terms of oversampling to 256 times, you can see how almost the density of color tells us something about the sine wave. We're almost looking at like looking down on top of the sine wave, you could view it as, I suppose. So that's really what we're trying to do. The modulator output is giving us this density information about where the average is, and with enough samples the average becomes a good representation of what's going on. So why is this important? We can view the quantizer as a source of noise. So this comparator is the thing that's going to be introducing the noise into our system, because it's making an approximation of the output. So if we say that we've got a noise signal coming in here, and that's the quantization noise, and it adds in with this thing here, we can start to do an analysis of this loop now for the noise from the quantizer, because it's being injected here, so it's running around this loop and then out, and the signal which is coming in over here. So now the noise and the signal are separate inputs to the system, which allows us to analyze it in a bit more detail. So if we do a superposition analysis and say with no signal, it's sort of a thought experiment really, and only noise coming in, and it's random noise with a certain distribution, then we can say that as far as the noise is concerned, it's seeing this amplifier here. It's going back round here. There's no signal coming in, so this is effectively just connected to HZ, which is then connected back again. So we've got this loop to analyze for the noise signal. Likewise, for the input signal, the one we're interested in, we've got this loop. If we suppress the noise source, we've got it coming through here. There's no noise source. It just goes around the loop and back into itself. So we can start to just look at the transfer functions for these two separate things, and then we can add them together again. So in this case, y is equal to u minus y times h of z. And if we then work out what is going on in terms of y plus yhz around the loop, we can end up with the standard transfer function of this equation, which we will recognize as being the standard loop equation for all feedback systems pretty much, that y over u, the output over the input, is equal to hz, whatever the function of that is, over 1 plus hz. And that's our standard sort of loop gain from any sort of feedback loop we're interested in. We do the same analysis over here for this slightly different loop, because the h of z is in the feedback effectively now. We do the same thing with e being the signal input, but it's our noise error, if you like. Run that through the same kind of basic analysis, and we end up with y over e. So the output with respect to the noise input is 1 over 1 plus hz, which is subtly different. It hasn't got this 0 in it. So we've got two separate transfer functions for the signal and the noise, and if we then combine them, because we were doing a superposition, we're assuming a linear system, we can add them together and find the overall response of the whole system is responding to the input signal and responding to the error signal, but there are different coefficients in front of this, or different functions in front of it. So if we can arrange for these to be separated, then we're onto something. So the important thing to notice is that there is a different transfer function for the signal and the quantization noise. So this is the transfer function for the noise, and this is the transfer function for the signal, and we can exploit this. We notice, for example, that if the magnitude of hz is large, then the signal transfer function tends towards 1. If we can make hz large, then h over 1 plus hz becomes a large number, 1, and we get a full transfer of the signal to the output. But if the noise transfer function tends towards 0, so the noise transfer function then tends towards 0, so we've made hz large. So if we make this large here, then this tends towards 1 over a large number, which is small. So if we can make h of z do what we want it to, then this becomes dominant, and the signal is then dominant. This becomes very small, and doesn't matter what the noise is, it's multiplied by a very small number, so it gets smaller. So it's a way of trying to separate out the noise and the signal, which is quite good, and it all hinges on the correct choice of hz. So in terms of signal response, we need hz to look like a low pass filter, because it needs to pass signals between 0 and a certain frequency, the maximum signal of interest. And it just so happens that in the z domain, 1 over z minus 1 is the definition of a low pass or first order low pass filter. So we just substitute that in for h of z and these things here, and then for the signal we end up with a forward transfer function which just boils down to z to the minus 1, which we now know is just a delay, so that's quite neat. And the noise, if we put exactly the same transfer function h of z in for the noise here and simplify that down, it becomes 1 minus z to the minus 1. So the first result is just a delay, but the second, if we know anything about z transforms, is a high pass function, because one of the rules for z transforms is that z equals 1, at DC z equals 1, and at high frequency z tends towards infinity. So you can put those two extremes in here and show that that's what's happening. So what happens is that quantization noise is not passed at low frequencies because of this function here, but it is passed, but signals of that frequency are passed. So we've actually suppressed the noise at low frequencies. Right, so we've run out of time really. So I will let you digest that, and we will pick this up on Friday and finish this off and look at noise shaping in a bit more detail when you're a bit fresher, because that's where the real interest comes. All this is just trying to justify it, but the noise shaping comes, and the concept of noise shaping, once you've grasped this, is really easy, and shows how wonderful some of these digital systems can be in terms of noise suppression. And then we can look at how we can actually take this idea and implement an A to D converter with it, because it's really quite exciting and quite advanced. And then we'll finish off with a little bit of work on D to A converters, but there's actually not very much excitement in a D to A converter, so it won't take us very long. So thanks for your attention, and I will see you on Friday.